In the first half of this lesson, we talked about the zero product property, and now we're going to move on to factoring polynomials by GCF. And hopefully that sounds a little familiar. That's greatest common factor, and it's going to be our first step in starting to factor polynomials ourselves. So the examples that we worked with in our previous lesson where we were using the zero product property, we were lucky enough that everything was already written in factored form. Okay, and so if we revisit those notes, we knew that we didn't really want it to look like this because the sum of two things equaling 0 is not helpful. We really want it to be as the product of a couple of things equals 0. So we want our polynomials in factored form. Luckily, as we worked through this, they were all already in this format. And today we're going to begin the work of how do we write it that way ourselves, okay, if it isn't already come in factored form. So to solve it, sometimes we need to factor the polynomial ourselves. So go ahead and write that down. So, which means write it as the product of other polynomials. So it might already sort of come in standard form, like this example here. And this won't be very helpful for us to solve and use the zero product property. So we would want to rewrite it in a way that it is written as the product of two polynomials. That's called factored form. Okay? So to start off, one of the simplest and most, like the first step, and even after we learn other methods, the first step is going to be to factor them by GCF if possible. So we're going to look for the GCF, which is the greatest common factor of the terms of our polynomial. Okay, and so that GCF is going to be the monomial that divides evenly into every term. That's really important. Okay, so highlight it, make a little mark on it, something to that effect. Okay, the monomial that divides evenly into each term. Now, one of the easiest ways that I can describe this, that I think helps students understand what it is that we are working with here, is the fact that when we are factoring by GCF, we're doing essentially the opposite or inverse of the distributive property. So let me give you an example. You guys are very familiar with the distributive property. So let's say that I had this monomial 2x on the outside and I'm multiplying it by x minus 7, for example. So if we were interested in simplifying this, we would take those two things and multiply them using the distributive property. We would understand that the 2x needs to multiply by both of those, and so that this is equivalent, or it's the same as, writing 2x to the second power. That's our first product there. If we do 2x times x, we get 2x to the second power. And then 2x times negative 7 would give us a negative 14x. And so these would be equivalent, and we would be able to use the distributive property to go from the factored form of this to the simplified form. And we've done that quite a bit. Okay? So you could think of what we're going to do today as essentially going in the opposite direction. All right, starting off with something that looks like this and trying to identify what goes into 2 and 14 that we can factor out. Okay, so you should be able to see this and say, oh, 2 goes into itself, it goes in evenly, and into 14, so I can factor out a 2. And then as far as x's, you know, how many x's do these guys have in common as factors that we can factor out? And it's only one x. This guy has 2 x's, this one only has 1, so together they only have 1 x in common, right? And so if we go from here to this, that is called factoring by GCF. It's basically the reverse of the distributive property, okay? So here's another example. They want you to factor out the greatest common monomial of 4x to the 4th power plus 24x to the 3rd. And so one of the things that makes this a little simpler, and I'm going to highly recommend, is that you separate this sort of work on the coefficient piece of it and then go back and work on the variable piece. Okay, so the coefficient piece of it is like elementary school. If we want the greatest common factor between 4 and 24, we want to know what is the largest number that goes into 4 evenly and that goes into 24. And in this case, it's 4. 4 goes into itself evenly, and it also goes into 24 evenly. So 4 would be our numeric GCF. As far as the variables, okay, that's the part that's a little more new, but I also think it's the part that's a little easier. Here's the bottom line, guys. Whichever is your lowest exponent, that is your greatest common factor. So your lowest exponent is your greatest common factor. So I have an x to the fourth and I have an x to the third. That's my lower power. So x to the third is our greatest common factor. Okay. And now think of it this way, right? If you don't have to do this every time, but it might help if you feel like you're getting stuck a little bit. What we're really doing kind of in our head is taking that 4x to the fourth, that first term, and separating it out into its prime factors. So 4 is 2 times 2, and x to the fourth is x times x times x times x. Okay, so if I were to separate this all out, it would be 2 times 2 times 4, start over. 2 times 2 times x times x times x times x, and there'd be 4 of those, right? So that would be this guy separated out into its prime factors. If I did the same thing with 24x to the third, 24 separates into 6 times 4, but then 6 separates into 2 times 3. So this would be 2 times 3 times 4. Let's leave it like that, right? Actually, this goes into 2. So it would really be, let's clean that up. So yeah, we would have really 3 factors of 2 and 3. That's just the prime factorization. So what I'm doing here is saying, oh, this is 6 times 4, but then this breaks up into 2 times 3, and this breaks up into 2 times 2. So we really have 2, 2, 2, and 3. So those are the factors that give me 24. And then x to the third is x times x times x. Okay, so you don't always have to do this, but I wanted you to see where this all came from. Because when we talk about the common factors, basically what do they have in common? Well, this has 3 x's and that has 4. So notice how in common they only have 3. Yes, this one has an extra 1, but the bottom one doesn't. So it's not a common factor, okay? This is really the emphasis why I wanted to do this, was to show you why the lowest exponent is always your greatest common factor. Because the one that has the lowest amount of that variable is going to sort of be the limiting agent here, okay? So I have 4 up here, only 3 there, so the most they have in common is 3. They have this one in common, this one in common, and this one in common. Same thing with our numbers. This has a 2 times 2, which is a 4, and this has a 2 times 2, which is a 4. Yes, this has other factors, but the other one doesn't. And again, I can only pull what they have in common. So if I identify what do they have in common, it's 2 times 2, which is 4, and 3 of those x's, which is x to the third power. That is why our GCF, in this case, is 4x to the third. And again, you don't have to do the prime factorization each time. You can sort of work that out in your head, especially after you get some good practice. But in the end, the next step is that we are going to divide that out, like we did that division of monomial at the beginning of the problem. So once we know that 4x to the third is our GCF, we're going to take this original and we're going to divide by that GCF. Okay, the GCF is going to stay out in front, and in the parentheses, it's going to be whatever is left behind. And you can almost see that here again in the prime factorization. Basically what we're saying, okay, if we pull out that 4 and those x cubes, what's left in this very first term? Well, it's just an x, right? So there's that x by itself that was not a shared factor. It's still in my parentheses. I would get the same this way. 4 over 4 cancels. X to the fourth over x to the third is just an x. So that's all that's left behind. And in this second one, 24 divided by 4 is 6, and x to the third over x to the third goes away. That is exactly the same thing over itself, so it cancels. So that 6 is the same as this 2 times 3 that they didn't have in common, that was kind of left behind, is what we have there. And so we're allowed to then write that common factor out in front and group this and rewrite it in this factored form, okay? And it basically represents the same as if I had, taken this and distributed. In fact, that's a really good way to check your work, is you could always, if you're not sure if you did it right as you start to practice this, you could always distribute this back in and you should get the original. And also, these guys should not have anything in common if you did it correctly. Okay, so let's just kind of put this in action and see a few examples here to help us process this. So we want to factor each of these polynomials. So we want to look for the GCF. That's the first thing, right? So look for the GCF. So let's start with our numbers. 7 and 2. Both of those are prime numbers. 7 only goes into 7, and 2 only goes into 2 here. So there's no GCF numerically other than 1, and we don't care about 1. So I don't have to worry about numerically speaking. These guys don't have anything that goes into both of them evenly. So then let's move on to the variables. Remember the rule, the easy rule, the lowest power. In fact, let's write that down because it is really helpful. Okay, so the lowest power is your GCF. Okay, the lowest power is the GCF. So this has z to the 7th and this has z to the 6th. This one is smaller. That's my GCF. So in this particular case, my GCF is just z to the 6th. Okay, so now our work is simply to rewrite this in that factored form. So what we're going to do is we're going to take this original and divide both sides by our GCF. Okay? And let's see what we get. When in this first term, if we factor out 6 of those z's, we still have the 7, because 7 divided by 1 is still 7. And then I had 7, I factor out 6 of them, I'm still going to have a z left. 7 minus 6 is 1, so I would still have a z to the 1 power there. And this one here, I would still have my 2, because 2 divided by 1 is still 1. That didn't change. And the z's are identical, so all 6 of these z's get canceled out, and I don't have any z's left. That's going to determine what goes in my parentheses, and then I just write my GCF out in front. And this is the factored version of that. So this is my answer right here. It's the same polynomial in factored form instead of in simplified form. Okay? And like I said, it should be equivalent, meaning that if I took this at any point and I wanted to distribute it back in, I should still get this original. So z to the 6th times 7z should give me 7z to the 7th. And it does. And z to the 6th times 2 should give me 2z to the 6th. And it does. And these guys right in here shouldn't have any factors in common, and they don't. So they're equivalent. This is standard or simplified, and this is in factored form. And because of the zero product property, we're going to want them this way. Okay, let's try it again. Let's try number 2 here. Let's start with our numbers. 24 and 8. What would be our GCF? What goes into 24 evenly and into 8? I'll give you a minute there. GCF. And if you said 8, you're absolutely right. Does 2 go in? Yes, but it's not our greatest. Does 4 go in? Yes, but it's not our greatest. Our greatest common factor is 8. 8 goes into 24, and 8 goes into 8. Okay. Now let's talk about variables. In the variables, the lowest power is going to be the greatest common factor. So in this case, it's just h. Okay, so that is my GCF. Perfect. So I can even write that in my answer now. I know that's what's going to be outside of my parentheses is that GCF. Okay. Now, to figure out what comes in here, you're basically going to divide that 8h from the first term and the second term. Okay, so let's write 24h to the 3rd plus 8h again, and we'll divide both of those by 8h. Okay. In this first term, 24 divided by 8 is 3, and h to the 3rd divided by an h, I'm just going to subtract those powers. This is a power of 1. So I still have 2 of them left, basically. Plus, and here 8 over 8 is 1, and h over h also cancels and is 1. Be really careful about this. That 1 is incredibly critical and important. Okay, if it's the entire term and you divide by, if the whole entire term is your GCF and you divide by it, it doesn't just disappear. Okay, you still have to have a 1 here for it to be equivalent to the original. So you've got to hold that 1 and let that 1 be holding that spot. If at any point I need to distribute this back in, that 1 has to be there for me to get an 8H here on the back part. Okay, there's our answer. Try number 3 and see if you can get that one correct. Okay, all right, now that we know how to factor by GCF, let's use it to solve with that product property. So I love that this is equal to 0, but I cannot use the property. It's not true that two things added together being 0 means one of them is 0. That's not true at all. So I can't just be like, oh, I'll make this 0 and that 0. Not with addition, but I can do it if it is the product of things, right? If they're being multiplied. So that's what I'm going to do. I'm going to rewrite this as a product of two things by factoring. So if I think about what do these guys have in common, well, 6 and 1 don't have anything in common, but I do have the k's, and the lower power is our greatest common factor. So here our GCF is k. I'm going to start going a little bit faster, okay? So once I know that, if you want to still show that division, that's a really good idea. We're going to take that polynomial and divide it by that k, and what that's going to leave us with, I'm going to put this on the outside. What that's going to leave us with is still the 6 here, and then one of those k's is gone, but there's still one left, plus, and then k divided by itself is just 1, and then I close my parentheses. But now this is equal to 0, and I can actually use it to solve. I could not use a 0 product property up here, but now that it's written as a product of two things, I absolutely can. So let's do that. Okay, now we can do it just like we did in the previous lesson. If this times this is 0, then either k is equal to 0 or 6k plus 1 is equal to 0. And then we solve. That's -1. And then we divide by 6. So our two solutions, this one was already solved, right? So our two solutions is that k is 0 or that k is -1/6. Leave that as a fraction. It's so much easier. There it is. Those are your zeros or your roots or your solutions. Okay, let's try the next one. Number 5. Again, we want to factor it first and rewrite it in factored form. I'm looking at 35 and 49, and I know 7 goes into both of those, and I'm pretty sure nothing larger than that does. So I'm going to say 7 is our GCF, or part of it. So 7. And then when it comes to my variables, my lower exponent is my greatest common factor. So 7n is going to be our GCF. Now when I divide this first term by 7n, and then 49n squared by 7n, this is what I'm left with. I'm going to have the 7n out in front, and then this division is going to guide me to what's left inside. What are those leftover factors? Well, if I had 35 and I still have a factor of 5. And if I had an n and I divided that n, then it went away and I just have that 5. The n's are gone on the first term. Here, 49 divided by 7 leaves me with a 7. And then n squared, if I divide one of those n's out, I do still have an n. Okay. So this is the same polynomial. Again, you could mentally, at least in your head, you could distribute this back in and you'd get this original. 7n times 5 is 35n. 7n times 7n is 49n to the second. And here I can tell they don't have anything left in common that I maybe missed or was left behind. So I'm okay. And so now I can just say, all right, this times this is 0. Well, the only way that can be is if 7n is equal to 0. I'm going to make a little line here so we don't get this. Or if the binomial 5 minus 7n is equal to 0. Those are the two scenarios that make this 0. And then we solve each one. So divide by 7. 0 divided by anything is still 0. So there's one solution. And for this one, I'm going to move the 5. We get negative 7n, is negative 5. And then we divide by negative 7n. So n would then be equal to a negative divided by negative is a positive. And I'm just going to leave this as 5 over 7 because that does not divide evenly. And decimals are lame. So there you go. No, they're not, but fractions are easier. So 5 over 7. So there's our two solutions. Okay. So this is all about practicing how to rewrite it in that factored form, because then you can do the work just like you did on the previous lesson. Let's try a couple more. Now, this is a good example. Look at number 7. it is not set equal to 0. Remember, zero product property, that is what it's all about. We really can't use it if it's not equal to 0. So my first order of business here, like the most important thing, is move things around so that it's equal to 0. Okay, so let's try that here. I want to move this 72x, so I'm going to just do the opposite sign, positive 72x on both sides, so that this entire side disappears and this is equal to 0. All right, now here, these are not like terms, so I cannot combine them. I'm just going to leave them right next to each other. Okay, problem number 1 solved. It is now set equal to 0. Okay, problem number 2 is that this is simplified and not in factored form. So now we look for that GCF. Okay, so if I think about, what's the GCF? What goes evenly into 6 and 72? I'm pretty confident saying 6 goes into 6 and 6 goes into 72. So that's going to be my greatest numeric common factor. For the variables, it's going to be, since they all have a variable, I can use a variable, and then whatever my lowest power is, that's my greatest common factor. So 6x here I think is going to do the trick, but I'll check. You can always check to be sure. So I'm going to take these two terms, divide them by my GCF, so that when I write it out in front of the parentheses, this is going to guide me to what's left in here. So 6 over 6 is 1. That goes away. X squared divided by x is still x. So basically the x's cancel, and the 6's cancel, and the x's, they subtract the power. In other words, I had 2 factors of x. If I pull 1, I still have 1 left. That makes sense, right? Put my little plus sign. 72 divided by 6. Okay, think about that. That goes in, I believe, 12 times. Okay, and then x over x, that's the one that cancels. Okay. And again, you can always do a quick mental check, because if I distribute this back in, I should be able to get back to the original. 6x times x is 6x to the second power, and then 6x plus 12 is 72x. So that is equivalent to the original, but now it is the product of two things and equal to 0, and now I can use a 0 product property. Okay, so if this times this is 0, then either 6x would have to be 0, or x plus 12 would have to be 0, and then we just divide each one. So one solution here is that x is 0, and here if we subtract the 12, the other solution is that x is a negative 12. There are the roots, or the solutions, or the zeros, whichever vocabulary word we feel like using that day. All right, let's try one more like that. Let's skip over to number 9. Again, it's not equal to 0 yet, so that actually becomes a main priority for us, is move that term over. So I'm going to subtract 21p on both sides. These are not like terms, so I leave them right next to each other. 7p to the second minus 21p. Nothing on the right now since I moved that. I'm going to look for a GCF here. So what goes into 7 and into 21? That would be 7. And as far as the variables, the lowest power is my greatest common factor. So 7p is going to be my GCF. Okay. So when I go to rewrite it, in order to figure out what's left, I'm going to take these two terms and divide them by that GCF to kind of be really careful and make sure I understand what's going to be left behind. So when I write my 7p outside, in this first term, the 7's will cancel, and I'll just have a p. Right? Because if I had 2 factors of p and I pulled 1 out, I should still have 1 left. And if I had a 7 and I pulled it out, I just have a 1 left. Minus, and then 21 divided by 7 is 3, and p over itself cancels. So these are the new factors, or the equivalent expression or equation in factored form. Okay. And if this times this is 0, we can now finish this off using the zero product property. One option is this monomial is equal to 0, and if I divide both sides by 7, I still get 0 here. So P equals 0 is one of our solutions. And the other is if we take this P minus 3 is equal to 0, and if I add 3 on both sides, I get P is equal to 3. So these are the two solutions for that one. Okay, we just said each factor equal. All right, let's finish out with a quick word problem here. It says a boy kicks a ball in the air. The height above the ball is modeled by this equation where x is time since the ball has been kicked. Find the roots, remember that's the same as the solutions or the zeros, when y is equal to 0. So we're going to insert a 0 here where the y is. Okay, so we've got 0 equals instead of y equals, and then we'll write the rest of it. So even though it's a word problem, it's really asking us to do the same idea. Okay, it's equal to 0. I'm going to look for a GCF here. Okay, for this problem, the GCF happens to be a 16, because I know 16 goes into itself, and I know it goes into 80. And an x, the lowest power, is your greatest common factor. Okay, so in order to rewrite this, I am going to divide it by 16x on both terms and rewrite it as 16x times. Here, I still have that negative and an x. Plus, and then here, 80 divided by 16 is 5, and x divided by itself goes away. So this is now the same expression, but factored out, and I can use the zero product property. So we've got 16x is equal to 0. If I divide, I get x is 0. That's one of the times since the ball was kicked, or the height of the ball. So at 0 at time, the ball was at 0 height. Yeah, so that which makes sense because you're about to get kicked. That's at the very beginning when it's still on the ground. And then for this guy, if we solve this, I'm actually going to just add the x to the other side. It's a little quicker. I get 5 equals x here. So that's our second. Okay, so explain what it means. Think about it. You have this ball on the ground and the person kicks it, right? If x is the time in seconds since the ball was kicked and y is the height, it would make sense that these two intercepts would tell me at 0 seconds the ball was on the ground, or was it a 0 height, and at 5 seconds the ball was at 0 height. Okay, so you could even express this and say, you know, this basically means the ball was in the air for a total of 5 seconds before it came back down, because the y height was 0 at these two times. At the beginning, and then after 5 seconds, the height was 0 again. So there you go. That is factoring by GCF that you can then combine with the zero product property.